Hello students, welcome back. The purpose of this lesson is to state and prove this theorem. This is really a fundamental theorem that we are going to be using, all the time in this chapter, and of course it'll come back over and over again in other chapters too. It goes like this. Consider a homogeneous system of m linear equations with n unknowns like this. Or equivalently in matrix expression like that. Now, if n is greater than m, which means if there are more unknowns than number of equations, then the system has a non-trivial solution. We already know there is a trivial solution. If these are all 0, then no matter what we have over here, something times 0 is 0. So a trivial solution always exists. But are there any more is the question. And if there are more unknowns than number of equations, then the answer is yes, there is non-trivial solution. If there is one non-trivial solution, and then consequently there are infinitely many because this is homogeneous. If you just multiply any scalar multiplication of a non-trivial solution, then that too is a solution. So if there's one, infinitely many more. Anyway, we have to prove that at least one non-trivial solution exists. And this is going to be a really hard proof. However, I'm not going to push it over to optional topic. This is the standard topic that everybody has to go through because this is so important. I know it's hard, but we'll have to do this. Now, in order to start this one, we have to use mathematical induction. So let's go to module 1 to brush up a little bit, and then let's come back. So let's go out and let's go to module 1. Okay, preliminaries, method of proof, and let's talk about proof by induction. By the way, this is a classification. There are direct proof and indirect proof. Among the direct proofs, typically we use proof by manipulation or proof by implication. Most of the time we have been using this one. For the proof of the algebraic rules for vectors and matrices, mostly it was this one. There were some of those implications here and there, but even there, the big chunk was proof by algebraic manipulation, at least so far. But all of a sudden, we are going over here, proof by induction. And let's brush up a little bit. So how does induction work? Assume there's a statement based upon some positive integer, n equals to 1, 2, 3, 4, 5, 6, or non-negative integers, starting from 0, 1, 2, 3, 4, and so on. First, we prove the base case, the smallest case. N equals to 0, it works out. Or n equals to 1, it works out. Now we assume it works out for n minus 1, and then prove for n. So if that's established, we're going to get this. We already proved the base case, n equals to 1. Because of that, n equals to 2 case follows. Because of that, n equals to 3 case follows. And then 4, 5, 6, and then just cover everything. That's how you can prove some statements based upon integers. Positive integers or negative integers. If it is in general integers, plus or minus, then you have to do it in both directions, going up and going down. In any case, this applies for discrete cases. Some example, okay, all right. Here's an example. Let's prove 1 plus 2 plus 3 plus 4 all the way up to n is n plus 1 over 2. How do we prove? Base case, when n equals to 1, I don't have to add anything. 1 is equal to, plug in n equals to 1 here, 1 times 2 over 2, yeah, it holds. So base case is trivial. And then let's suppose this is true for n minus 1, so plug in n minus 1 in place of n. So we get this expression. Substitute n by n minus 1. So n minus 1, this is n minus 1 plus 1. So we get that. Assume this, and then prove it for n. How do you do that? 1 through n minus 1 is this expression. So add n to both left-hand side and right-hand side, and then apply algebraic manipulation. From here is proof by algebraic manipulation. So apply this, and then take common denominator and do some substitutes, do some simplification, and we end up with the right-hand side. That completes the proof. That was the simplest possible case. The kind of proof we are going to be doing here is much higher level, but still it follows the same idea. Proof by induction, where we assume n-1 case and then proof for n. Whew. Such a long introduction. Okay, finally let's begin. We are going to be using induction on M. Okay, M linear equations. Okay, alright. Now, let's suppose m equals to 1, which means I have only one equation here. You see, m can be arbitrary, 1, 2, 3, 4, and m is 4, then there are 4 equations. M is 17, then there are 17 equations. The lowest possible case is just one equation. Just one equation with, say, 5 unknowns. In that case, do we have non-trivial solution? That's something we want to establish. Ready? Okay, here we go. We have just one equation, so we don't have to write first row, second row, third row, all the way to 10th row. Just one row, that's enough. Okay, and then how many unknowns? We have n unknowns, n is greater than 1, more than or equal to 2. Case 1, if all the coefficients are 0, a1, a2, a3, all the an, all these are 0, then any x1 through xn will be a solution. So that's going to be a non-trivial solution. Anything will do, but in this particular example, I just took this as an example, 1, 0, this one. That's a non-zero vector, and then plug into this example. Remember, all the a's are 0, and x1 is 1, all the others are 0. So what I had, that's 0. 0 times 1 is 0. All the others are 0 times 0. So yes, we get 0. So it's okay. And then of course there are infinitely many more, but I don't care. I want is to establish one non-trivial solution, and we found out, and that's it. The simplest of the simplest case, if all the coefficients are 0. But then again, that was too simple, too trivial. What if there are non-zero coefficients mixed up here? In that case, there will be at least one non-zero coefficient, whether it's going to be a2 or a17 or a105, whatever, there will be one. Now, here is some ingenious trick that we are going to be using over and over again in this course and also in abstract algebra. If we have, say, 10th number is non-zero, we can simply change the order, rename, and then bring it over to the very first. Without loss of generality, we can assume a1 is non-zero. Yes, we can do that. Otherwise, all you have to do is appropriate renumbering or renaming. Because it's just renaming, we don't lose any generality. And that's not the only way we use without loss of generality, but in this course, probably that's the only chance. That's the only time we're going to be using this without loss of generality. If there's something else here, bring it over to the first, or sometimes the last. So without loss of generality, by renaming if necessary, I can make this one non-zero, yes, and then I can solve for x1 by flipping all the others to the other sides I did here, and then divide by a1. Why can I divide by a1? Because I can assume a1 is non-zero without loss of generality. Let me repeat again. Even if a1 is 0, there gotta be some ak that is non-zero. bring it over to A1 by just renaming it. So without loss of generality, we can always assume A1 is non-zero. So we can divide by A1. We can solve for x1 like this. And will that help? Yes, it will. X1 through Xn, we can put arbitrary numbers in there. But let's keep it simple. You can put it all ones. X2 is equal to 1, X3 is equal to 1, X4 is equal to 1, all the way to X1 is equal to 1, all 1. And then if I plug in all ones here, then X1 will be this blue number. So X1 is determined by the others, and the others are all 1. And that is a non-trivial solution. Plug this number back into this original and see if you get 0 equal to 0 by doing appropriate simplification. I'll leave that checking to you students. Okay, so much for the base case. M equals 1 case we did. Next, a little bit harder part, induction. Let's assume this is true for m-1 equations, okay? And then let's prove for m equations. Ready? Okay, all right. Now, case 1, if every coefficient is 0, let's go back. If all the coefficients are 0, then we can put in anything, any number in there, especially all ones, for example. So non-trivial solution exists. Okay, let's go to case 2. There is a non-zero coefficient somewhere here. Then without loss of generality, we can assume as A11 is non-zero. Well, if there is some non-zero element somewhere down here, what do? Simply renumber it, rename it. Bring that x700 into x1 by simply switching and renumbering it. And A of whatever into A11, again by renumbering. Just switching the order. Renumbering, renaming it. So without loss of generality, I can always bring that to the top. And then we do something similar. From the very first equation, we can solve for x1 because I can divide by A11. Shall I do that? From here, this equation, from that equation, okay, let me copy and paste that equation over here. From this equation, from here, keep this and flip everything to the other side and you're going to get that. Right? And then divide by A11. Yes, I can, because without loss of generality, I can assume A11 is not 0. And this is what we get. Something pretty similar to what we did before, except that the indices are more complicated. But in any case, we successfully solved for x1. Now, let us plug this back into our system. Previously, it was just one equation, so plugging it back was rather a simple deal, but this time it's gonna be a work. Let me show you. The first equation I de-emphasized in gray. Why? Because we already used up. And solved for x1. So it's not there anymore. And then I'm plugging this into all the other equations. Second, third, fourth, all the way to mth equation. Make sense? We got this from first equation. So plugging it back into the first equation, you're going to get 0 equal to 0 or 17 equals 17, something trivial. It's not going to help us. I have to plug into the other equations. And how many other equations are there? m-1 equation. Does it ring a bell? m-1 case, we assume yes. So we're going over to induction. So we plugged in all those, this expression into this, and then the next, and all the way there. I highlighted in appropriate color, blue color. And then let's rewrite that. So this x1 is this expression. This x1 is this expression, and so on. Just rewrite those, and that's what we get. Why am I losing some orders here? I want this to align these equalities and oh, what did I do? Oh, never mind too much about the start point. Sorry about that. Okay. This one we plugged into x1 here, and the next x1 here, all we have to do is x1, which I just did. So how many unknowns do I have? I have n minus 1 unknowns. x2, x3, x4 all the way to xn, n minus 1 unknowns. How many equations do I have? M minus 1 equations. So, did we assume n is greater than m? Yes, there are more unknowns than number of equations. We both reduce 1, n minus 1 unknowns now from x2 to xn, and then m minus 1 equation from second equation to mth equation. So we can apply so-called the inductive hypothesis. We assume that our conclusion is true for m minus 1. So that's true, which means there is a non-trivial solution. I don't know what that is, but it's gonna be something complicated. I don't care. I'll just name those as x2 bar, x3 bar, all the way to xn bar. Not all of them 0. Some of them may be 0, but not all of them should be 0. And that'll satisfy this system of linear equation, m minus 1 equation. Now we have the solution from x2 bar, x3 bar, all the way to xn bar. And how do I get x1 bar? Well, right here. That's the relationship we got. Remember where it came from? From the original first equation. Yeah, first equation here. First equation. We solved for x1 and got this relation because we got the numbers for x2, x3 all the way to xn, which are x2 bar, x3 bar all the way to xn bar, with these are numbers, not variables anymore. Not all of them 0. So x1 bar equals to those. That'll give me x1 bar. That too was determined. And then couple those with all those, and then we have x1 bar, x2 bar, x3 bar, all the way to xn bar. Not all of them will be 0. And we got the candidate for the non-trivial solution. Now, will this be really non-trivial solution? As a matter of fact, yes indeed, you don't really have to go back and check. Although I wrote the final checking is left to the students. You don't really have to, because x2 through xn satisfy these equations, but these equations that equivalent to these original equations. So yes, x2 through xn, they all fine. And x1, that's the only problem, but it came from this gray equation by that process. So yes, that too is okay as well. But if you want to actually plug those in and then do some brute force computation, go ahead and do that. I'm not going to stop you. In any case, that completes the proof. We use mathematical induction. Just a brief recap. We established for one equation. And how did it do that? Case 1, all coefficients 0, that was too trivial. And then at least one non-zero, then without loss of generality, we just put it into first and solve it. And then the others are anything, ones, and that worked out. And then by inductive hypothesis, we just repeat it, and then we have everything. That completes the proof.